Okay, so everyone, welcome back. We are going to continue with the discussion of Azad Gainutdinov about interchiral algebra. Please, Azad, go ahead.
Okay, thank you. So we last time we stopped about this analysis of asymptotics of these Virasoro generators, which are certain combination of Temperley-Lieb generators, and in the so there is this parameter n, which you should think as it parameterizes the momentum, and the asymptotics of these Virasoro generators close to when momenta is in the units 1 over L, when it's close to 0, we extract left and right chiral anti-chiral Virasoro generators from the combination of, let me maybe remind you, what were these HN? Yeah, maybe. Okay. Right. So I have actually, I mean, it's so HN is just sum over these exponents when Q is momenta, and it's just parameterized by n as n pi over L. And then you can consider a family of like such a Virasoro formulas. So when L is 0, it's just EJs. When L is 1, it's a commutator EJ with EJ plus 1. And for general L, it is long commutators. So it's useful to analyze the asymptotics of all these sort of long range interaction terms and then taken as a Fourier transformation. But the most important ones, just if you analyze, for example, if you want to extract Virasoro generators, it's just H0 and H1. In this case, it was not H of n and P of n, right? And as I said before, that it's if we want to extract all scaling operators, because of this dispersion relation, it's important to analyze also the operators with momenta close to pi, or in a sense close to infinity. So let me introduce now. So I had these Virasoro generators like H0. It was sum over all this exponent of Temperley-Lieb generators, and L is number of sites. Let me now parameterize now consider L minus K. So in my so if you see this this drawing, so this L minus K, when K is finite, that means that I'm concentrating on the momenta close to pi. So if momenta is pi over 2, this is where energy goes to infinity in the scaling limit. And to momenta close to 0 or to close to pi, I get some non-trivial scaling states, scaling operators. And that's where you extract. So when you focus on momenta close to pi, you extract the new scaling operator. So here, so this Virasoro generator defined as previously with these exponents. After scaling, it produced me these infinite sums, which is like Virasoro. The Virasoro was psi alpha plus times psi beta, but here now the chiral and antichiral sectors are mixed. So we get, and the difference from the Virasoro is now they are coupled not with symplectic form, but with symmetric form, as alpha beta is now a symmetric form. And these are case modes of what I call interchiral fields. Later on, we will see that actually from these Virasoro type generators, you can extract a family of operators like this. I will call them SKL. So they are a combination of the same quadratics, but with the special coefficients 2m plus k to the power L. So these are case modes, Fourier modes of this interchiral field of conformal dimension 1, 1. And all these guys, they are Fourier modes of Virasoro descendants of that field. So let me introduce this field. in terms of these derivatives of fermionic fields, we have this small psi's. So they are primary fields of conformal dimension 1, 0, and 0, 1. So I have this product which is non-chiral. So one psi is chiral, the other is antichiral, and they are coupled with a symmetric form. Remember that energy momentum tensor was very similar like this. Maybe I give a formula below, not here. The energy momentum tensor was J alpha beta, psi beta. So it was chiral combinations with symplectic form. Here is a non-chiral, but with symmetric form. And this is SK0 I obtained from the lattice, focusing on the momenta close to pi. These are just Fourier modes of these fields. And the whole family are Fourier modes of certain descendants of this field. Right, maybe let's talk about, so we've got these fields. Let's talk about the algebra they generate. Let's spend some time to look at the commutation relations. So because it's in terms of fermions, it's super easy to calculate commutators. So again, this SR index 0, it's like it corresponds to the primary fields. So RS, they are Fourier modes of my interchiral fields. Let me remind it again. This one. This is what I will call interchiral field. It's with respect to Virasoro with respect to Virasoro action, it's just primary fields of conformal dimension 1, 1. Right. So if you look at the commutators of these Fourier modes of these interchiral fields.
No, I mean, just before we start computing, I mean, a priori from your construction, so you recover this interchiral field,
yeah,
as a limit of as a certain limit of a certain element of affine Temperley-Lieb algebra, right, and so on. So just from this fact that you recovered it like this, what can we say a priori about these commutation relations that you are going now to compute explicitly? Like, can
I deduce it from Temperley-Lieb algebra? Or?
No, probably not. But just like, what is the general feeling that what I'm expecting to find? So, for example, does it mean that fields that we will obtain by commuting this guy with anyone else are also going to be somehow element of this inductive limit of the Temperley-Lieb algebras is guaranteed? So what can we say generally?
Yeah, we can say that right. So let me say, right. For example, if you look at the if you're interested just in the vacuum sector, in the vacuum representation, like imagine we get all these fields and we apply on the vacuum state. We're interested what kind of Virasoro representations we get, because these are at least these Fourier modes I present, these operators, I can prove that they generate all possible scaling operators. So which means that if you start with the reducible representation of the Virasoro algebra, you look at its spectrum, left-right Virasoro, it might be decomposed onto many reducibles with respect to Virasoro algebra. But because all these guys, they come from affine Temperley-Lieb. So if I start with a reducible representation of the Virasoro algebra, in the limit, it should stay reducible with respect to this interchiral algebra. Okay, this is what we certainly can prove. And for example, you take any irreducible representation of the Virasoro algebra, there are different ways how to extract the spectrum of it. So for example, characters of left-right Virasoro algebra. You see from
representation of Virasoro algebra is not going
sorry. Representation of the affine Temperley-Lieb.
Yeah, okay.
Take any representation of affine Temperley-Lieb. For example, any irreducible. And then there are different, even in more complicated cases, like not this pre-fermionic theory, but here it's even rigorously mathematical. You can prove that you take irreducible representation of affine Temperley-Lieb, you look at the scaling states, and you can extract the characters, Virasoro characters, and you see that there are many primaries contributing, or it's decomposed into many irreducible representations of the Virasoro algebra. But because we started from affine Temperley-Lieb, and these new operators that recover all scaling operators you get in the limit from affine Temperley-Lieb. So all these states should be also form a reducible representation for all the scaling operators. If you want, this is a full set of scaling operators from affine Temperley-Lieb. So if you start with irreducible, in the limit, it should be irreducible representation of this algebra. So from this analysis, you can see that these SKs...
You are using a bit interchangeably the words fields and generator. I'm a bit confused because...
by fields, I mean modes of the fields. So I can prove that. So there is this one field, interchiral field.
Mm-hmm.
And it has these modes, Fourier modes, they're just as simple as this.
Okay.
I'm saying that this, then you take commutators of this. You will generate, it will be expressed into many new operators, right? But they all come from, first of all, from affine. So the Lie algebra, this field generate, it will be hugely algebra. And it will be the full set of scaling states.
Okay.
So in particular, the scaling limit of the reducible representation of affine Temperley-Lieb, it will be again a reducible representation of this algebra.
Okay.
In particular, the commutator of this guy with itself, it produces you left and right Virasoro generators. So
okay,
they are in a sense descendants. They are in a sense descendants. So this guy is a fundamental, in a sense, more fundamental than Virasoro, because commutators with itself, it produces you left and right Virasoro. How we can see it, again, as I mentioned, there is this SP2 symmetry in a field theoretic sense. Because it's CFT given by the action, you have these Noetherian currents that the charges of these Noetherian currents give you a representation of a Lie algebra, SL2 or SP2. It's exactly that, SP2. It's a global SP2 symmetry. And it's a symmetry in the sense that it commutes not only with Hamiltonian, but it commutes with energy momentum tensors. So the Virasoro respect this symmetry. But from this analysis, you can easily check that this operator does not respect the symmetry. Let me maybe show you the vacuum sector just to, as I talk about the symmetry. So this is the symmetry, SL2. So there are these are charges of Noetherian currents, SL2 symmetry. So with respect to this symmetry, so this is a vacuum module. It was what was denoted in Yifei-Haytok by W0Q square. This is irreducible representation of affine Temperley-Lieb, which is sort of where vacuum lives. And in the scaling limit, with respect to the left-right Virasoro, it decomposed onto infinitely many product of infinitely many irreducible representations of the Virasoro algebra with Katz label J1 and then for the anti-chiral sector J1. So it's kind of diagonal sum. And with respect to SL2 symmetry, J is a spin. So, okay, J is right. J is a spin actually. Spin minus 1. So J equal 1. It's 1, 1, 1, 1. It's identity operator. It lives in the spin zeros multiplet. And then the next term, J equal 1. So it's a field 2, 1, 2, 1. This is
where are you? I mean, you are taking this a bit out of the head. Where does this follow, this equation?
Okay.
There were some equations for commutators that you skipped. Are you going to talk about them?
Yeah, well, I'll talk about them. So this formula comes from because I can construct a fermionic basis in the vacuum module. And I know how my Virasoro generators act in terms of fermions. So I can construct in the limit, in the scaling limit of irreducible Virasoro representation, where vacuum lives, the vacuum module, I can construct, I can diagonalize Hamiltonian, right? So I can extract the Virasoro characters. And this is what I'm just telling you, that with respect to left-right Virasoro action, the scaling limit of the vacuum module is a direct sum, infinite direct sum of irreducible representations of the Virasoro algebra. And I was just wanted to talk a little bit about the symmetry. So every component for fixed J, it lives in a J's multiplet for this SL2. So here there are representatives from the different multiplets. And from the lattice point of view, because I know this is irreducible for affine Temperley-Lieb, so the scaling operators coming from affine Temperley-Lieb, they should mix different multiplets. And this way you see that the operators that mix different Virasoro components in this direct sum, they should break SU2 symmetry. And that's exactly what interchiral generator does. So you can mix all these different Virasoro components only by the fields which have Fourier components which break SU2 symmetry. Where was it? And this is this combination. You can just calculate explicitly, for example, that it does not commute with SU2. Okay, let's study the commutators. So the commutators of this of the modes of this interchiral field, you see they produce Virasoro. So label 0 means it's just standard Virasoro. You see they produce, if you take RS, it produces you minus 2S, and then Virasoro mode R plus S, and then the anti-chiral and chiral, they produce independently. But also they produce descendants. So what is called by one in terms of, if you remember, we discussed Virasoro modes. If you just put L to 0, it was this symplectic form paired with this quadratic of symplectic fermion modes. But I have more general generators, n to the power L, when sum is over n. These are modes of descendants of Virasoro. Like imagine, take some derivatives, higher derivatives of the energy momentum tensor. So they are basically modes of Fourier modes of derivatives of energy momentum tensor. That's it. So they are just Virasoro primaries. And
no, I don't understand. So
no, but for example, take derivative of t of z. What will be Fourier modes? Because take derivatives, you will have n to the power 1.
I mean, what does it mean? I mean, if it's just Virasoro, then is this field a product of Virasoro generators?
No, no.
Is this generator a product of Virasoro generators?
No. We're talking about this one, right?
Yeah, this one.
Yeah. So so if L is 0, this is just modes of energy momentum tensor, right?
Yeah.
If L is 0. Okay, this we solve. If L is 1, so energy momentum tensor lives on the level 2, right, in the vacuum module. It has conformal dimension 2. Now apply L minus 1 to it. You have apply L minus 1 to T of Z. To the state corresponding to T of Z. You will get a state at the level 3. And the field corresponding to this state, we have a pattern state correspondence.
But why don't you call it simply L3? Why do you invent a new letter for it? Because if it's L minus 1 acting on L minus 2, then we commute, it becomes L3 plus something. So
sorry, 0 means, so I have additional index 0. So it labels Virasoro descendant. So if L is 0, it's just energy momentum tensor. If L is, for example, 1, it's
no, but we are talking about algebra. I mean, these are algebra elements. Let's just suppose that there was no this S.
Right.
Then all our algebra is made out of Virasoro generators. There are no other generators. Now you are saying that there is a new generator. What is this new generator? But it seems to be existing already without S. It's just by itself. It has to be Virasoro or something like that.
You mean, no, this one is not coming from the Virasoro.
It's not coming from the Virasoro.
No, it's not coming from the Virasoro.
Why do you call it the descendant of Virasoro?
No, but they're Fourier modes of descendant of energy momentum tensor.
Descendants of what kind of descendants? Virasoro descendants or something?
Yes, Virasoro descendants. Yeah, the Virasoro descendants.
I'm sorry, Virasoro descendants
of energy momentum tensor.
Virasoro descendants.
Okay, for example, apply L minus 1 to energy momentum tensor. I mean, derivative of energy momentum tensor. It's a new field, right? Of control dimension 3. Take its Fourier modes. And you will get, it will be LK1. And so on. So this is what is generated by, but maybe let's go to OP. Maybe it's
no. I mean, this is important. Let's discuss this because I mean, I want to understand Because these derivatives of Virasoro exists in any theory.
Yes, yes.
So why are we not discussing then these derivatives of Virasoro as extra charges in any theory? Why do they appear only in your theory? Can you explain why? Take any textbook on CFTs, they will tell you that is the Virasoro algebra. They won't tell you that there is a new generator.
They will not tell me, but I see it from the commutators of my interchiral fields.
Okay, can you explain why in textbooks they don't say it? Is it because in other theories they don't exist, these generators, or they always exist and the books are wrong?
Of course they do exist. I mean, like it's just, you say why I don't need probably, you see, the fact that I think we should distinguish between universal enveloping algebra and the Lie algebra. So I think if you do, how to say it better. So this higher LKs, so these Fourier modes of Virasoro descendants, you could do analysis of the CFT with respect to these descendants.
But Azat, I don't think these are the modes of the derivative of t. The modes of the derivative of t you multiplied by k to the L. This construction here with n to the L, you can only do it because you have the fermions to begin with. This is normal order, for instance, of derivative of fermions times fermion. That give n. For instance, if you pick L equals 1, I guess this is just the normal order of deep psi alpha psi beta.
Deep psi alpha.
You take the derivative of the fermion, not of the stress tensor.
Yeah, but it will be a new field, right? And
but it's
not.
But
you can only build it in this theory. You need the fermions. You can't do this if you don't have fermions to begin with.
This makes more sense. It's a new field specific to this. It's a new.
If you just take the modes of the derivatives of t, you just take, instead of ln, you get n times ln. It's just, it's not a new generator.
Let me think. No, but I should be. So if I act on the vacuum, so the state I produce it. Let me see. So you're right. It's a deep C times C. My energy, but let's take my energy. My energy momentum tensor is J alpha beta psi psi, right?
So but if you take the derivative of this, you'd get two terms, and then you're going to get n times plus k minus n times, and you just add k goes out of the sum, just multiplies the whole thing, so you get nothing new.
Let's look at OPE. We will see because this should be consistent with OPE, right? And
no, but Azar, we haven't seen the full algebra. You're going to the OPE.
Okay. Let's discuss then. When I discuss OPE, let's discuss the nature of these operators.
Let's discuss the nature of these operators later.
Later, right? So I have these operators coming from these Cousin-Liouville formulas in this limit, which are interchiral, and just by direct calculation, you produce left-right Virasoro, but you produce these extra guys. Okay. Now you ask, what is the Lie algebra of these extra guys? So when you and it's closed. So if you extra guy ln1 with ln1, you get of this type. You see. And now it's like in the Virasoro, but it's quadratic. It's not m minus n, but it's like n minus 2m. Plus you get a previous guy, L0. Bar, non-bar, they commute, of course. And L1 with L0, it produces you also L1 and L0. But it will be linear in terms of modes. So it looks more like Virasoro. But the point is that when you now I have to calculate S with L1, for example. So when I calculate, you see S with L1. So here take L equal 0. If you take L equals 0, so this term disappears. And what you get, you get R minus S mode, and you get S1. So Virasoro modes with this SR0 modes, they produce higher version of these guys. So this is what I denoted here. What was it? SKL. Yeah, right. SKL. Right. So I have analogous to these LKLs, but now coupled with the symmetric form, and they are psi alpha m, psi beta m plus k, and then they have L's power of sum of the modes again. So I have this is the whole family. Okay. So for L equals 0, again, it was the Fourier modes of that interchiral field, phi to 1, phi to 1. The nature of these ones we will discuss later also, but...
where are the currents of SL2 in this algebra? I don't get a bit confused.
The currents of SL2?
Yeah.
No, but SL2, I don't have currents of SL2 here. Why I should have currents of SL2?
Of SP2, there is a SP2 symmetry, so there has to be a current of SP2.
Yeah. But SP2 is a symmetry, right? It's something that commutes with Virasoro energy momentum tensor, but it will not commute with interchiral fields. As I say, the interchiral field breaks the symmetry. SP2.
Okay, so there is this extra current, but it's trivial, kind of. You don't discuss. Okay.
Mm-hmm. Right. So when you commute these new operators S with Virasoro, they produce higher version of S. So the general formula is here. You see. So you start with SRL, you commute with standard Virasoro, it produces you L plus 1 version. Plus there are previous guys, or corresponding to lower k with this particular binomial coefficients. So the Virasoro just generates you. It produces you more and more new type of operators, and right. And the general formula SRL with LSL prime. You see the general commutator. It can be explicitly computed, but it's just okay. This complicated with this nice binomial coefficients. It will be again written in terms of only S-type Fourier modes for certain indexes. K plus K prime, it's a type, and mode R minus S. And okay, and the most complicated is SRL with SSL prime. You see, so the different types, they produce you only Virasoro type operators. You see only L's for K running from 0 to L plus L prime plus 1, but these coefficients are they're coefficients of this particular expansion. So this is what I calculated just explicitly. So it's a bit, the formula is quite tricky. So the algebra, if you want, the basis in the algebra is not just simple as ln, because as I start with SR0, it generates me new fields. So the basis in the Lie algebra is LKL, LKL bar, and SRL. And all the commutation relations are given here.
Okay.
Azat, may I ask a question?
Yeah.
So I guess you can build local fields by resumming these modes, right? So you have a field S0, a field S1, etc. Are they scaling fields? And like, if yes, what is?
Can you repeat the question?
So out of all these modes, I can build local fields, right?
Yes, yes.
So I have an infinitely many. I have a S0, S1, S2.
Yes.
Are they all scaling fields? And if so, what is their dimension?
Yeah. I will talk about them when we discuss.
Okay, sorry.
Representations of theory content.
Okay, thanks.
But Azat, can you comment, because this starts looking like it's something extremely special for free theories and so on, because you see these S's, they have integer dimension, as is evidenced by the fact that when they commute, you get Virasoros.
Yeah.
So how can something like that be true in the Potts model where this field is not going to have an integer dimension, this field that you call interchiral?
This is much more complicated. So, but
I mean, not just much more complicated. Do you have a scenario how it can happen?
Wait. So, for example, in a minimal, in a minimal model for Ising, you have similar story. Okay,
but in the Ising, there is also a field of dimension one, so one can imagine. But if you just have a field of general Q, then there is no dimensions, there are no fields of integer or half integer or rational dimension.
No. Yes,
So what's going to happen?
I don't know. So because I don't have access to calculate explicitly.
But then how do you have the right to conjecture that there's going to be there interchiral algebra or whatever?
Because in that case, we know spectrum. So we have this vacuum model where vacuum lives. This irreducible affine Temperley-Lieb representation. And then you can realize this module inside an integrable system. It's a twisted XXZ model. So using integrability, you can actually numerically, solving by Tanzat, you can access to the low-lying excitations. And it's not proven, but you see from this analysis that the vacuum module will have decomposition over the Virasoro algebra, same as I was showing here. So the vacuum module.
I mean, that I might believe, but in your comments on Slack, you made a very specific claim that the field phi12 generated this interchiral algebra also for Potts. How can this happen if the field phi12 for general Potts doesn't have an integer dimension? Do you have a scenario for that?
What I can, so scenario is just again by analogy, so that I know that from this spectral point of view, the vacuum module, which is irreducible for affine Temperley-Lieb algebra, it has exactly the same decomposition, but just of course different conformal weights, but in terms of Katz labels, it's the same. And I expect that taking all scaling states, all scaling operators, again, they should make this infinite direct sum irreducible. And the guy that make it irreducible, it's the one living in the second component, x21, x21.
Yeah, but in which sense is it going to act? Because you see, in your theory here that you described, it was very special that you had this operator S of integer dimension, so you just decompose it in modes. And then you can view modes as really Lie algebra elements. Now, in a general CFT, if you have fields of non-integer dimension, when you start acting, of course, you can still like act with the field, multiply it with some other field, but then there's going to be OPE with non-integer factors of Z. And you cannot just, there's still an action in terms of the OPE, but the OPE algebra, unlike the algebra that you're considering here, is not a Lie algebra. It contains these factors of Z. And I mean, it's so the action.
I don't know. Well,
it's not a Lie algebra action. So
but
how can this
expect the diffusion rule? So here is the OPE, but OPE so S is phi21 bar, right?
Yeah.
And I can look at OPE with itself. So here I see only the vacuum sector because from fusion rules, what I expect, I mean, in this case, I can calculate, but in general, I expect that the chiral field phi21, it has self-fusion phi11 and phi31. And here it's product of antichirals, but we expect the fusion should be antichiral field. I mean, it should be identity plus phi31 times phi bar 31. So I expect this sort of fusion for non-chiral fields. I cannot prove it, but I expect this sort of fusion. And if I have this fusion, that means that taking consecutive OPEs of the field phi21, bar phi21, I should generate all these direct summands in this direct sum.
But you have to consider fusion of this S of phi21, not with just with itself, but with other fields. Because if you want to consider the action of this phi21 on someone else, you have to consider that sort of fusion.
But first I would like to understand if it generates just considering its OP with itself if it generates all components in that direct sum, which I can see here explicitly, calculating OPs, which is very easy because of fermions. But from general fusion expectation, I see, at least if I apply fusion phi21 bar phi21 with itself consequently many times, I can generate these higher terms. So that's why I expect that it's just enough to take, and you see, because of fusion phi21 bar phi21, again, with itself, it produces you identity, and you see the identity OP here. You see, with OP, you produce 1 plus energy momentum tensor, T bar, plus descendants. These are just descendants you can calculate of T. Plus, there are kind of mixed terms. You have dt, and here Z minus W over Z bar minus W bar. So this is a vacuum part. Plus, you have fields corresponding to phi31 times phi31 bar. And this is an interesting question, actually, to prove it or to give an argument why fusion of phi21, phi bar to 1 should be, as I say, identity plus phi31, phi bar 31.
No, but even if this is true, I mean, this is still like, seems to be much less than what we need for this to be useful for POTS, because we should be able, because, okay, if we're just talking about fusion, okay, yeah, POTS model has some fusion and we can try to work it out and so on. But for this to be useful, there has to be really some Lie algebra behind the fusion algebra, because the fusion algebra is very complicated. If in order to make this work, we have to work out the fusion algebra, it's very complicated. The only hope is that somehow behind the fusion algebra, there's a Lie algebra, which is much more constrained, which governs the fusion algebra. For example, in the same sense as Virasoro governs the fusion algebra of CFTs, but Virasoro is a Lie algebra, so it's not. So the question is like, do you think that this phi21 somehow is going to, once we start fusing it with other fields and there's going to be complicated fusion algebra, you think it's going to reduce in some sense to the Lie algebra? Is this the hope?
Yeah, I don't know. The Lie algebra represented here, I don't. No, I don't even expect that this Lie algebra will appear exactly like this Lie algebra representation will appear in generic central charges, like for Q-POTS model, or at least I don't see why.
Is your central charge fixed to be -2?
Yeah. Here's the central charge is -2.
So this stress tensor you formed out of the symplectic fermions. This is the stress tensor of the full theory, not just a component, not just like a part of your theory.
Say this again. So I have energy momentum tensor T for chiral antichiral.
That's the full energy momentum tensor.
Yes. It's full energy momentum. Okay. Yeah. Yeah, I don't know how to better describe this interchiral algebra better than just fusion algebra or OP algebra of this particular primary field.
So if it's just a fusion algebra, then this is not doesn't explain this mystery that our colleagues have seen, that somehow the OP coefficients of the different fields inside this module. So you expected, I thought that there was a belief that there is some Lie algebra and there is some module of the Lie algebra in some sense, which they call interchiral module and the OP coefficients of different fields inside this module were related by some simple relations. And so the hope was, I think, that the reason why the P coefficients were related is because there is some nice algebraic structure behind. And so these relations are kind of similar to the same relations as OP coefficients of different Virasoro descendants. But for that expectation to live out, to live up to this expectation, there really has to be some. Yeah, I was hoping at least that that this Lie algebraic structure would survive for general center chairs. Maybe not exactly this, maybe some, of course, different algebra, but
maybe it makes sense. I never did it, but maybe it makes sense to do the same sort of analysis, for example, for models with another central charge, even if it's minimal model, like Ising case. Central charge is different, but it could be that it will be representation of some central extension of this algebra, because here central charge is -2, so you don't see central extension terms. They might be hidden somehow. But maybe if I do the same analysis for the Ising, again, I'm saying like there is this Kusalor paper when they did this Ising spin chains and basically did here when you can again extract from Kusalor left and right Virasoro, and again they missed this part that you have to also analyze Kusalor generators for the momenta close to pi. I mean, like on the other side from infinity, if you want.
Okay.
And this again in the Ising case also gives you interchiral algebra generators. Just kind of minimal model, and you get interchiral algebra. But in that case, because it's minimal model, interchiral generators, they will link finitely many, because you will have only in the bulk, you will have finitely many direct sums of finitely many irreducible representations of left-right Virasoro, and they will link them into one irreducible representation. So in principle, same analysis, it's even simpler, could be done, and just to see what kind of algebra I get. What kind of structure constant?
But for example, for the Ising model, this field 512 would it be the epsilon field?
Yeah, it's an energy operator. Yes, it's phi to 1, phi to 1. Yeah, phi to 1 is the energy operator. Yeah.
Okay, so
so basically, we interchiral field. It will be just this non-chiral energy operator, epsilon bar.
Okay.
And I think, I think for every Potts model, it should be phi to 1, phi to 1. It has a sort of lattice meaning as energy operator.
But can you at least confirm that all fields in this, so there's like the most basic check for this picture. Okay, so if you look at all the fields that you expect to be contained, for example, in this vacuum module of the Temperley-Lieb.
Yeah.
So you're saying that you would like to conjecture that they're all generated by this phi to 1.
Yes.
So, yes. But so does it mean that, well, phi to 1 is h to 1, h bar to 1, so it has dimension. So does it mean that all fields, all Virasoro primaries in this module, they have dimensions of the form something plus a multiple of h to 1? So the dimensions should add.
Yes.
Do the dimensions add just like naively? Or is there any subtlety about that? Because in the OP algebra, the dimensions don't add, of course, because there are factors 1 over z and so on, which compensate for the dimension.
Right.
And then it's a mess. I mean, it's not a mess, but it's as complicated as it gets.
Right.
For the Lie algebra, we have every generator has a nice dimension, and so we know exactly which dimension that we will get when we act with this generator. So if we know the fields, the dimensions of different fields inside of this interchiral multiplicator, then we can see if the dimensions are just multiples of something, differences or not. If they are not, then it basically excludes the Lie algebra structure and means that we have some more complicated algebraic structure. Maybe Linnea can answer this. Is she
Yeah,
right?
She looked at these Cousallor formulas much more seriously for these generic cases. Yeah.
Yeah, I'm just explaining it like composite, like for the sorry for the microphone. I know, I'm sorry.
There is this strong noise, but maybe the discussion could be because Linnea will participate in this discussion on Thursday.
Yeah, I think we should probably stop now. Okay, we should thank and then we will resume again on Thursday and see. We will get somewhere little by little. Okay, thanks, Azad. I'm going to stop the recording now, and then in a few minutes we have a lecture.
Mm-hmm.